All right, so we have an example of work and energy and something that's actually involving friction here. So we have a food shipper pushes a wood crate of cabbage heads, total mass M of 14 kilograms, across a concrete floor with a constant horizontal force F of magnitude 40 newtons. In a straight line displacement of magnitude D equals 0.5 meters. The speed of the crate decreases from V initial of 0.6 meters per second to V final of 0.2 meters per second. A, how much work is done by the force F and on what system does it do the work? And then B, what is the change in thermal energy of the crate and floor? So we have a crate on the floor. It's being pushed with an applied force F. And then, of course, because there is an applied force, but it's slowing down, we know that there has to be a force of friction here. Because if there was no friction, then that applied force would cause an acceleration in the same direction, and the crate would be speeding up. So we have a force of friction in the opposite direction. Now, of course, we also have a normal force and we have a force of gravity, but those two things are doing no work on that crate. So for part A, it says how much work is done by the force F, the applied force, and on what system does it do the work? So for part A, we want to know the work done by the applied force F. So that's going to be F times displacement times the cosine of theta. Now, of course, we know what F, our applied force, is. We know the displacement as well. And then we'll just say we know that applied force, they don't give us an angle, so it's in the same direction as the displacement. So that means that is going to be a cosine of 0, which is just a positive 1. So we end up getting work is equal to the force, 40 newtons, times displacement, 0.5 meters, times the cosine of 0. So we get the work done is equal to 20 joules. That's the work done by our applied force. Now it also says on what system does it do the work? So that applied force is doing work on the box, all right? However, we are slowing down. So we have a non-conservative force of friction acting on this box from the floor. So because of that, we're actually losing kinetic energy, even though we are applying a force to the block. And again, that's because we have a non-conservative force involved. So what we can do here is we can include that non-conservative force with the other equation that we learned. We know that the work done by that applied force will equal to the change in kinetic energy. In this case, it's just kinetic energy because we're not being elevated or anything like that. So we're changing kinetic energy, and then plus the change in thermal energy as well. So we just found the work being done by that applied force. And like I said, in part A, it is done on the block. But again, if we include the floor, then we can also include that in our equation like we are doing for part B. So in part B, we're saying, okay, that work is being done on the block floor system. So we know the work being done, the change in kinetic energy we can find because we know the mass of the block and we know the initial and final velocities. So I know work is equal to the kinetic energy final, which is going to be 1/2 times mass times final velocity squared, minus the kinetic energy initial, 1/2 times mass times initial velocity squared, plus the change in thermal energy. Now we are finding the change in thermal energy. So I'm going to solve this equation for change in thermal energy, and then we'll plug in our numbers. So we get change in thermal energy is equal to the work done plus the initial kinetic energy minus the final kinetic energy. So change in thermal energy will be equal to the work done, which was 20 joules, plus 1/2 times the mass of the block, which was 14 kilograms, times the initial velocity, which was 0.6 meters per second, and we'll square that, minus 1/2 times the mass, 14 kilograms, times the final velocity, which is 0.2 squared. Sorry, I dropped my units. I was running out of room. So 20 plus the quantity, 0.5 times 14 times 0.6 squared, minus the quantity 0.5 times 14 times 0.2 squared. And I end up getting that my change in thermal energy is equal to 22.24 joules. Now, the other way that you can find this change in thermal energy is we also know that the change in thermal energy is equal to the force of friction times displacement. So you can find force of friction because you could find the acceleration that with our change in velocity and our displacement, and then using Newton's second law, you can then find the force of friction that causes that acceleration as well. So you could use this equation as well to solve for that change in thermal energy.